Good afternoon, everyone. Hope everyone enjoyed the lunch, and hope all of you have a great rest. Now, we start the afternoon session. Here we'll be introducing the first speaker, Daniel Russell. He's a Philip H. Geier Junior Associate Professor in the Decision Risk and Operations Division of the Columbia Business School. His research lies in the intersection of machine learning and online decision making. Mostly falling under the broad umbrella of reinforcement learning. Outside academia, Dan works as an Amazon scholar applying reinforcement learning to supply chain optimization. He previously spent 5 years working with Spotify to apply reinforcement learning and large language models to audio recommendations. Dan completed his undergrad studies in math and economics at the University of Michigan, doctoral studies at Stanford University, under the supervision of Benjamin Van Roy, and worked as a postdoctoral researcher at Microsoft Research in New England. His research has been recognized by the Erlang Prize, the Frederick Lanchester Prize, a junior faculty interest group best paper reward, and first place in the George Nicholson student paper competition. Now let's welcome the speaker.
Okay, so I'm really excited to be here. It's been a great event so far, and there's kind of so many people in the audience who I'm honored to get to talk to. I'll give, there's kind of a broad ambition and worry, I guess, in the room around AI and what it means for us and what does it mean for the field and so on. And I'm giving a talk that's really about two papers of mine and trying to call out common threads in the research direction and so on. But maybe it doesn't speak necessarily to broad questions about what OR is as a field and so on. So sitting up there, I did think for the purpose of having questions at the end, I'd make a few broad comments, teetering on the edge of making people mad. So let's go for it. One thing that, and I've been a part of a few of these. So there's something at Stanford, something at NeurIPS, something at Columbia, all around what does AI mean for us? And one point I want to emphasize to certainly PhD students in the room is I think you should not be worried but excited a little bit. Like it's just the best time to be a researcher, is my feeling, and to be in academia. Okay, and so some reasons for that, and also to be broadly in this space. Okay, and some reasons for that. One is if you're kind of a systems person, then the best time to be thinking about systems that get implemented at a societal scale and that have safety constraints and incentives in them and so on is when stuff's changing. So if AI is getting deployed all over the place, then stuff is changing, and no one knows how to do it. This is very exciting to be a slow, careful thinker in that world. Okay? Now, the other thing is that the decision sciences in general have been very impactful intellectually, and also at times quite impactful in practice, but have been deeply handicapped. Okay, I make decisions all the time, basically never solve an LP in my life. Because most decisions, the inputs are unstructured. They're images, they're text, there's someone's face, their emotional reaction, their conversations, and the outputs are unstructured. They are also text. They are songs we make. They are driving motions. It's very rare to work with numbers in the world, right? And so if suddenly technology is changing, then this field has enormous scope, 100 times bigger than it had before, 100 times. And the thing that worries me, though, is that the field is, instead of going after that opportunity, going to define itself by tools. Okay? If we define ourselves as the people who write LP solvers and ask and view AI as a fixed chatbot that exists, it was created from the sky, but it's largely fixed, and it's going to wrap around our LP solver, then we will be one tool out of 100 that people who make Claude call, right? And I think it's very important to get that interface right. It's very, very important. And it's very useful, but it shouldn't be the only thing we do. Okay, so I hope that the PhD students in the room, like some fraction of them ask, how do we do algorithmic decision-making at scale, massive scale that is efficient for the world in a modern way, in a very different way than anyone could have thought about 20 years from now, 20 years ago. I'm sorry. Okay, so that'll be my little spiel, and then I'll give a normal research talk. Okay. So here we go. So I'm going to talk about two papers of mine, and I didn't really even realize this totally when I was executing both of them. But they have a kind of common theme to them that I guess I am drawn to, and the dream is to be looking a bit at this gap. Okay, and on the one side of the slide, I have shown here offline sequence prediction, the driver of pre-training of most AI development. Okay, and what you're doing really is you're imagining a world where data comes to you passively. It comes in complicated forms, right? So you split an image or text or protein or whatever into sequences of tokens, and you model the joint distribution of all the data you're seeing, these complicated objects, by predicting them in sequence. Okay. Now on the right, you have a paradigm of interactive decision-making. It can go by different names with different lingo, but I'll use RL lingo. Okay. And in that, there's a decision maker who interacts with the world. Their actions produce outcomes. Okay. And so through this interaction, they are both learning something, like their actions produce feedback, and they are maybe having influence that is persistent across time. Right? And I think that the thing on the right captures a lot of how we live. All right, if you are an intelligent being, that's kind of how you live. Right? But it's got challenges that are not there on the left. It's got challenges of distribution shift. Right? When you take actions in a different way, it brings you to settings you weren't in before. Okay. And it's got challenges of active exploration, of kind of needing to do things in order to gather information, not because they're useful immediately. And it has challenges of credit assignment, of kind of things work out, and you don't know what it is that you did exactly that led them to work out. So if you look at the picture this way, it kind of feels like, at first, like everything everybody's been building on the left doesn't fit what I wanted, okay? Now, why ask this question? Right, one reason to ask this question, asking of what core primitives of sequential decision-making can kind of be reduced to sequence prediction. A reason I'm going to sort of ask that, one thing is it's cute, If you can show that you solve some decision-making problem just by sequence prediction, it is cute. All right. Now, I think it's also useful in certain respects. Okay, so out of sequence modeling at scale came things that we just haven't seen elsewhere. There's just massive scale of engineering investment to make this run. Just nothing else is receiving any kind of concentration around it, so it's useful to write your problem in a way that sits within that whole engineering framework. That's just a practical benefit. Now, out of this comes a multimodal fluency, so models that can speak in English, in code, in different languages, and produce images, and so on. And I don't know of another way to get that. And lastly, out of this comes an ability to transfer knowledge and procedures. Anything you're doing as a prediction problem, as a decision-making problem, it's not like some alien gets dropped and knows nothing about how the world works. Okay, so the transfer across tasks is just built in. All right? So this hints that this kind of technology would provide useful implementation. Also, if decision-making reduces somehow to sequence modeling, intellectually, it suggests that models that are trained by sequence modeling may have inherently already some decision-making capabilities we care about. All right? So that's why you would ask this question. I think it's worth just flagging here this disambiguation. I do not mean in this talk, how do you apply the alphabet soup of PPO, GRPO, something else PO, to make language models better. I really mean, how does sequence prediction itself, the task of predicting the next outcome, align or not align with making good decisions? All right. So last kind of disambiguation here, I do not mean like zero-shot prompting. That is very cool and quite humbling when it works. You know, I've seen RL problems that no one could solve, that someone solves by throwing in manuals about how to play the game and carefully writing a prompt to, you know, get the computer to play the game. And it is embarrassing and humbling that that works better than anything we knew how to design. It is a sign that we should be leveraging this technology to solve decision-making problems, but I don't know how to write a good prompt. I'm not gonna do it. Okay, so let me go into these two papers. The first is something that I wrote sleep-addled over the last month or so, kind of after the usual things I was doing, because I was pretty excited about it. It appeared on arXiv yesterday, so I've never actually spoken really a word about this out loud. We'll see how this goes. And this is the title. So I'm talking about success conditioning as policy improvement. All right? Now, success conditioning is a term I'm coining for an operation many people are doing with sequence modeling. And policy improvement is a phrase that would appear in dynamic programming or reinforcement learning. Okay, so I'm trying to tie a bridge in this way. All right, so what is success conditioning in my lingo? I'm trying to wrap up a procedure that looks like this. Maybe you've been acting in the world, and sometimes the thing you do works out. Sometimes it doesn't. So you could come up with a labeling. It could be that a person looks at it and assigns a labeling. It could be some fixed coded up rule that says this trajectory worked out, this one didn't. And then we're going to filter to the ones that worked out. Okay? And now, what do we know how to do with sequence models? Well, pretty much we know how to imitate. We can imitate language. We can imitate driving. So now let's apply our sequence model, update it to imitate the actions that were taken along the trajectory that worked out. Maybe before I imitated some other data, now I'm going to imitate the stuff that worked. Okay? Any questions here? So I will make it slightly more precise, but roughly makes sense.
If I replace the word trajectories with data points, what do I do in this?
I mean, I guess you could have a one-period trajectory. It's a little less interesting, but you could have a one-period trajectory.
But is there something temporal or sequence aspect of it?
Yeah. I think many of these will have a major temporal aspect. So it might be like a computer use agent where it, writes stuff and then calls to do a search query and then gets the results and then keeps taking actions and then calls again and then it gets a coding bug and then it fixes it. So there's kind of a sequential aspect. I don't know. I don't know if people are doing this, but I roughly have in mind that you might be like doing self-driving, and then some of these work well and some of them don't. So there's a sequential aspect, I guess, built in.
Is that comparing pieces of trajectories versus comparing trajectories would be different, right? Or identifying trajectories or pieces of trajectories might not.
God, I got it. I will kind of sidestep that and think of this as being framed nicely as you have medium length trajectories that are divided. Task goes for a while, it ends. Task goes for a while, it ends. Right. Okay, so you see this in two different places, at least under slightly different names, but I think they're very much the same thing. One is in RL lingo, there are things like decision transformers, okay, which are trying to implement this idea. Okay. And now all over the place in kind of LLM alignment and agents, so on, there are these pipelines where you do rejection sampling, you remove the unsuccessful trajectories, and then you do SFT, and supervised fine tuning, so you imitate the trajectories that worked. Okay. So the principle here is learn to act as you would have given it worked out. Okay. And firstly, note that what's a little uncomfortable here is that you are conditioning on the future, which is not a thing we're usually allowed to do in probability. Okay, so given it worked out, what is it I would have done? All right, so this is a decision transformer. Let's go through this quickly. This is an example, a paper from a few years ago that had a huge following then in RL. It beat a lot of other kinds of RL policies that were doing more explicit optimization. And roughly, it works like this. Okay? Roughly, you learn a model that says, given I got a very high score in the game, what did I do? Okay. And so you take the future, you throw it back in and condition on it, and then you try to predict what you did. All right? So in the lingo of this talk, I will say this is trying to reduce policy optimization to sequence prediction. Okay? And I will stand here before you and tell you, when this first came out, I said, this is ridiculous, and pretty much ignored it. Because I'll show you an example where this is a very bad idea. All right. But as I guess you can tell, I'm rethinking that point of view. All right, so here's principled understanding of this is difficult, and it's partly difficult because the culture in most of these spaces is to propose ideas that make a level of sense, talk about them fairly informally, and provide empirical results that are sometimes very strong and sometimes not strong. Okay, but the level of language is maybe not what an ORC student is used to. Right? So maybe I shouldn't do this because it's recorded, but here we go. Here's a comment from the abstract of the decision for transformers paper, and I think it's fine. I mean, they mean this informally, but trying to make it formal is a little hard. Okay, unlike prior approaches to RL that fit value functions or compute policy gradients, decision transformers simply output the optimal actions by leveraging a causally masked transform. Okay, now people saw this and okay, let me double check. Let me put on my theorist hat. And quickly, a number of papers pointed to concerns, especially in stochastic environments, say, okay, this is not a route to constructing the optimal policy. Condition on a good thing working out. What did I do? Not optimal. Okay. And some raise even a bigger concern, which I will refute a little bit, that you are conflating luck and skill. Things worked out, maybe you just got lucky. You can't condition on a future luck. It's in a way that the papers are hinting that this is deeply unsound also. Okay. So let me try to formulate this rigorously to try to understand, okay, if this is principled and it is optimizing something, then what in the world is it actually optimizing? And here's the model. I'll use MDP type notation. We have a trajectory tau, which is a sequence of states and actions. Now, the notion of, and then it ends. Okay, and the cleanest formalism for studying this kind of problem is to think of a problem where you eventually hit a terminal state and you end. All right, so once you hit this set of terminating states, problem's over. Right? And strangely, not always recognized, kind of built in to the notion of success conditioning is that there is a binary measure of success. Okay, if you're going to do this, so I'm going to assign each trajectory a label for whether it ended in a successful state or ended in an unsuccessful one. All right, and important notation, pi 0 is going to denote what's sometimes called the behavior policy. It's the thing that generated the data before. And probably the operating mathematical definition of success conditioning is this one here. I will play an action in the current state. According to the probability that is what the behavior policy did, conditioned also on the trajectory having been successful. So I take something about the end and I put it down there. Make sense? Now there's an equivalent, a definition here that looks much more like a sequence modeling, where you are trying to predict, minimize loss in predicting the next action given that you are along a successful trajectory. Okay. So I'll mostly skip here, but you shouldn't overrate the fact that I called something Markov. It's just notation. The state could be the whole history. And so in a language modeling example, your actions just append to state, and it keeps growing. Okay. So let me kind of break this, right? But looking back, I think that the way in which it breaks, I overstated. I dismissed this too early. Okay, and so here's the operating failure mode. Right? And it's as simple as I know how to make it. You take a problem where the trajectories are length 1. Okay, so you take an action and then it's over. There's 2 possible actions. One action succeeds with probability 0.505, and one succeeds with probability 0.495. Okay? And somehow, these are just scalings. It just kind of shouldn't matter. But there's 2 actions, one's better than the other. Clearly, what you should do is learn the better one and try to pick it. Right. But what happens with success conditioning is that built in here, success is not that strong an indicator in this problem. Okay? So if you condition on success, you do make it a little more likely that you pick the better action of the 2, but only very little. Okay, so you do not learn the optimal policy, which would be all the mass on arm 2, but you move very slightly in the direction of the arm. All right, so here, success conditioning is going to close 1% of the optimality gap. And the sense in which it's failing is that it's hardly moving. All right? I will formalize in a sense, it's a little like a gradient step that moved with a very small step size in this case. Okay? Made things better, but you can observably see I ran this procedure and nothing happened. Very little happened. So that's the failure mode. It's not the worst failure mode. Okay. So here's, in general, I'm going to interpret exactly what this success conditioning operator is. And I'm going to show that success conditioning is very similar at a high level to many other things that reinforcement learning researchers have been circling around. It is a conservative policy improvement operator. So it is maximizing the improvement you can get over the behavior policy, subject to a constraint that you cannot venture very far from the behavior policy. Okay? It's like a kind of smart gradient descent in policy space. And so it's the more precise statement. It is the exact solution to a trust region policy optimization problem, right? Which has this unique geometry. So the RL literature, basically everything is this KL divergence constraint. And it just so happens that's not what this is. Some kind of chi-squared divergence constraint. And so it's a little unique. And the other thing that's unique is that the amount by which you move is not a hyperparameter. It's not a step size that you tune or that Atom tunes for you. It is intrinsically defined by some kind of property of the environment. And that's something I'm going to identify and call the action influence. Okay. So how much does conditioning on success move you? I'll hit you with a bunch of notation, which is familiar if you read this kind of paper, and otherwise it is a lot. Okay, so there's conditioned and unconditioned notions of the probability of success. Unconditioned, chance a policy succeeds in this problem, is denoted by rho. Okay. In MDBs, you also have the chance that you succeed conditioned on state. That's the value function that I'm denoting by V. There's a chance that you succeed conditioned on the current state you are in and the action you take right now, and that's often denoted Q. Okay. And all of this is just kind of like notational bookkeeping. Very common here is to work with these things that are called advantages, which are the difference between Q and V. So you normalize by taking out kind of the average across actions you might pick and see what's the delta of this action versus what I would have done otherwise. All right. Now, what is this action influence measure that I teased before? It is, I'll define this as the influence of the next action draw under the behavior policy, and it's measuring how much that draw of the next action is changing your success probability. Okay, and what it is precisely is it's the coefficient of variation of the Q function. Okay. So, I don't know if you're in ops, coefficients of variation show up a lot. This is a measure of how volatile success is as a function of your randomly drawn actions. Okay. So this can be small for one of two reasons. One is your actions may not matter. If your actions just don't matter very much, okay. And the other is it could be small because there's really no randomness in which action you pick. All right, so if you always pick action 1, then conditioned on success, you picked action 1. All right, and there's no action influence in that case either. Does this make sense? All right, so working toward making my theorem precise, this is a trust region policy optimization problem written in kind of generic form. The usual form that shows up kind of all over the literature, TRPO and PPO and mirror descent policy optimization, and actually also direct preference optimization looks a little like this, and so on, is the following. You maximize some kind of local policy improvement. I'll go into what L is in a second. Subject to the divergence between my policy and the behavior policy being less than some radius. So to instantiate this, you have to determine how do you measure divergence, both like how much importance do you place on staying close in this state versus that one, and in what geometry do you measure divergence? Like what does it mean for two probability distributions to be close? And lastly, what radius do you pick? Okay, so this is kind of a vague template. You can imagine, and people have done this, many, many papers coming out trying to propose how to set these different ones. I'm not going to argue in favor of one or the other, I'm going to say what success conditioning is. Right. So just kind of quickly, so you fix, now I'm going to tell you what that L is. Right, what's the objective? It's maximizing. And basically, it's the gradient. Okay, it's the policy gradient. So what's going on here is if you think about changing your policy, the impact of that can be quite complicated. So a natural thing to do is to tailor expand your objective. You come up with, well, a 0th order term, which you don't change. A 1st order term, which is this linear thing based on the gradients, that is kind of a locally good representation of the function. And then a remainder term, which you hope is small if you don't move too far. Okay, usual thing in 1st order optimization. Okay, so what trust region optimization is trying to do is basically move in that 1st order, to make that 1st order term good, without going so far that you degrade the remainder. All right. And for people who are curious, in this particular case, it's a lot more interesting than general nonlinear optimization. That 1st order term is like exactly what people would have studied in dynamic programming anyway. Okay. So this links to what is in my DP class. And this 2nd order term is precisely about distribution shifts. It's about the fact that if you take actions many, many times that are different from what you did in the past, it takes you to new parts of the system that you may not understand well. Okay, so there's kind of a rich study of this whole object. All right. So here's my formal theorem. Success conditioning, which says imitate my actions along successful trajectories using a sequence model, can equivalently be viewed as solve the following optimization problem. Maximize 1st order policy improvement subject to staying close to the behavior policy. Close is measured through a chi-squared divergence. You can look up in my paper what that means. Okay. And the radius has to do with action influence. The action influence in your problem is small, can't change much. Action influence, or sort of this signal in success, is strong, you can move a lot. So, kind of omitted from the talk, but how do you just roughly think about what this constraint's doing? Roughly what it is telling you is that it is fine to forget actions that you used to play. So there can be things in the behavior policy that you just don't like anymore and that you stop doing. Okay? But it is very strong about penalizing you for trying things in the new policy that you did not previously do a lot in your old one. That makes sense. So if there's something you never did in the past in your data, this kind of success conditioning cannot cause you to explore it. Okay. So I would view this as delivering somewhat on that promise. We have this procedure that just uses sequence models to decode what action you picked. But if you look at it hard enough, it solves some kind of an optimization problem that I could have imagined being in a dynamic programming textbook. All right? And so it's under the hood. It's not literally that it's calling a solver. It did it implicitly. All right. Now, I'll kind of move on to the next part, but I'll flag that the paper has more in it. The result I think is probably most useful and cute is that several things are exactly equal. So the amount by which the policy improves is governed by that action influence exactly. And a diagnostic for how much better things got is how much you move. Right? So if you do success conditioning and you end up with the same policy pretty much that you had before, you didn't improve. If you do success conditioning and your policy is very different, then you are much better than you used to be. Okay. Paper does a number of other things about estimation error and dealing with return thresholding, this thing that's in decision transforms and so on. But I think for the purpose of the reduction, I've shown you what I mean. Okay. Does this make sense? So I think this is one case study that I would argue is hinting at this idea that I think was not true back 10 years ago, that sequential decision making was like classification. Really not true. But sequence prediction is a very deep thing. And this is one case study where policy improvement can be rewritten somehow as a sequence prediction problem. Surprising. Now I'm going to go quickly through another case study that does this kind of reduction in a very different setting. For those of you who are ORC PhD students who attended my seminar last year, you saw this talk. It was longer, probably confusing, so maybe this will be a quick look again, all right, with this slightly different lens that I now have. Okay.
So in the previous thing, if I ask,
Yeah.
What about generalization? If you, let's say, get policy improvement, then does this have a guarantee on, doing well on similar tasks or similar
I don't know. I mean, the way I would, it's in a certain sense, it's baked into the framework, because you could always call the initial state a descriptor of the task. Right? So in many of these problems, I mean, and in fact, I think this is often how it would be done, that the first state just describes, like I think in that language modeling example, the first set of states are just a description of what you're trying to do. And so in that sense, there is generalization. What is unclear to me how to think about is how you generalize outside of the training distribution entirely. I can't speculate about that. I don't know why that works so well sometimes. Okay. So the case study 2 is going to look at a different core primitive in sequential decision making that doesn't look like it's there in prediction. And that core primitive is going to have to do with exploration. Okay, so what this paper does is it looks at these types of bandit problems that involve some text to make them hard, okay, and solves them with an algorithm that just relies on having an offline learned sequence model. Okay, so in that sense, it is for a particular class of sequential decision-making problems, is sort of like a reduction, where the thing that quantifies your uncertainty and enables you to gather information that resolves your uncertainty is sequence prediction. All right. Okay, so I'll kind of go quickly here and just say that this was, I mean, Sasha knows this well, I guess. This has not been true. Okay, this has often not been totally true, that it was enough to say, like, have a classifier to then solve an interesting bandit problem where you have images as your arms. Okay, so you could do image classification. This is an ad with this sentiment, yes or no. But you couldn't create images that are going to get engagement and then learn which ones did. Okay, different problem. And I think the fundamental gap is that in interactive decision making, you often need to know what you don't know. Okay, and you all do this yourselves constantly, right? You decide what you don't know, then you open a book to learn it. You decide what you don't know, you talk to someone about it. You decide you've never tried a food and you go try it. It's pretty hard to actually get that out of most machine learning systems. It's driven me nuts for like a decade. Many people who've done this, have worked on this kind of problem, have been bugged by the difficulty of getting older style neural networks to quantify their uncertainty. Here's a paper called Deep Bayesian Bandits Showdown that says, that it highlights a lot of these issues. And here's what they come up with for being the best benchmark that they can find. You take a neural network and you pretend it's a linear model. Okay? Because if you just took the last layer features, you could just say it's linear regression. If you freeze everything with the last layer, and then you solve bandit problems, pretending your model is a linear model for uncertainty quantification. Makes sense. So using rules for linear Gaussian updating and so on. You don't have really a neural network-friendly way to do uncertainty quantification. You reduce back to classical statistics if you want to do that. Okay. And I'm not going to try to benchmark against that. I'm just going to say that that is not a path to AGI. Okay. It's just clearly not in keeping with the ambitions of the field, if that's the status of things. So here we're going to find a different route that that rests on sequence modeling instead of classification. Okay, and just so you have this in mind, the problem we'll have to illustrate ideas, something so important, but is a news article recommendation problem, where your system operating at scale, every day, new news articles are released, and you want to figure out whether they're a good match for a user cohort. You have the text of the articles, but you're still not sure which ones are very engaging. And so you interact with people across the day, and interacting with them early, with the first users, is going to provide information, potentially, about whether the articles you've been showing are engaging, allowing you to zero in on what's working and not working. Okay? Now, why this problem? Well, one, it has text. Two, it has a data set. And three, I think it is capturing the idea that uncertainty is never fully resolved, because there's always a new day with new articles. So just kind of a teaser here. Here's how our algorithm works, illustrated through Thompson sampling. Throughout the day, so far, we have a bunch of articles that have been released. We have a bunch of users. We have a bunch of data that we've gathered from recommending things to users. And there's a bunch of missings, because most people have never been recommended anything. Okay? And the way our procedure works is it uses autoregressive generation from a sequence model to fill in the missing data in a very calibrated way. Okay? And you can think of that like a simulated scenario of how the world could realize. And we use that simulated scenario, and using Thompson sampling logic, this is kind of orthogonal to our paper, what that procedure then does is it acts as if the simulated scenario is correct, causing it to explore, takes an action, and does this again. And the key part of the loop is that generating missing data. So what I'll try to do is just to illustrate that imputing missing data step and why that's the right thing. And then I'll kind of close. So here's the kind of the core idea, is the way these problems have often been framed, at least people like me, is that, well, to act in the world, you need to and to gather information, then the core primitive you need is you need to know what you don't know. I can't decide about the value of gathering information if I don't even know up front, like what I'm uncertain about and what could resolve if I do gather more information. Okay. So many of these problems, people like me, have been framed in terms of Bayesian inference, right, which gives you precise uncertainty quantification. And I'm going to try to rewrite some of that using sequence modeling primitives. So here's a temporary focus then, dropping the bandit framing. Let's just focus on a simpler problem where you get a passive stream of observations that so far are limited, they're incomplete. So I have some observations, y1, y2, y3, and I want to be able to say what I know and don't know given the information I have so far. Okay. So in the news article setting, this could be like I have a news article, I have text about it, I've had 3 users interact with it. Given what they've done and the text I have, is this an engaging article? Do I know? Do I have enough information? Okay. As an abstraction, it's very general. This could be that I have a patient, I have metadata about the patient, I have applied several kinds of different tests to the patient, and I want to know, does the patient have diabetes? Do I know? Do I not know? What are the risks? Okay. So there's 2 kinds of uncertainty in a problem like this. One kind of uncertainty, often called aleatoric uncertainty, is due to just inherent idiosyncratic randomness. If I show something to a user, they might just be tired and they don't like it. If I apply this medical test, it's noisy, it may not work very accurately. Okay, might have to try it again. There's another kind of uncertainty, which is often called epistemic, which might be something like, well, this is just one article. I've had thousands in the past, millions in the past. Some fraction of them engaging, some are not. There's some kind of prior here. Right? Same with the patient. What fraction of people like this have diabetes? Okay. And so the core of this is you're going to have to, any coherent solution to this problem is going to have to somehow keep these straight. These different notions of what's making you uncertain. All right, so here's what the classical Bayesian approach. You specify a latent variable, okay? And then people fight with each other over decades about what the meaning of this, but specify a latent variable that might be the health profile of the patient. Or here it might be something about the properties of the article and how engaging it really is. Then you specify a prior. So in this setting, this is something like, first I have to know what eta is, it's some kind of vector, and I need to know how to specify beliefs about that latent given the unstructured information z. So given the article text, what's the probability it has this kind of latent? Okay. And then I need a likelihood about the way that governs the chance of different kinds of interactions given the true property of the article. And this lets me do inference on the latent given my information. Okay. And so across time, I update my beliefs about what kind of article this is. And the core inference problem that then becomes a subroutine for many different algorithms is something like posterior sampling. Given a latent and a quantity of interest, this could be something like how many, the like rate plus 0.2 times the click rate. Given an article and a quantity of interest, draw samples from my current posterior and plug them in to get samples of the quantity of interest. So hopefully this is familiar. This is not really ours. This is just any economist would have written it this way. Okay. So here's an alternative view. And once you accept the alternative view, sequence modeling, I think, becomes almost immediate. So here's the alternative view. Forget Ada. It's somewhat hard to deal with. I don't see it anyway. And I'm going to focus exclusively instead on data that I may potentially observe. And I'm going to frame my quantity of interest, my inferential target, as being a function of the data we could potentially collect. Right? So in the news article setting, this is something like, imagine I had recommended this to all 100 million users. Had I recommended it to 100 million users, I could compute how engaging it was, and I would be done. Okay. For the medical setting, this would be something like, if I had run a barrage of costly tests, I would know quite a bit about this person's health status, and I will call that the target. Right now, I have very little data. If I had a lot of data, what would I know? Okay. So I will frame that as the inference question. I want to know some function of a complete data set. I have an incomplete one. How much do I know given the incomplete? Okay. And let's solve that problem. Okay. Sequence modeling, I'm going to claim, is basically tautologically the answer to that problem. I'll specify my function here, f, as being a reward, just to reuse this slide. Okay, so f became r. Okay. So let's say I have a news article. I have two observations. I have its text, and I'm wondering, does it perform well? So what is the function? What's the average reward I would have gotten among all people in the population? Well, the reason I don't know the answer to that is that I have so much missing data. Okay. So what I'm going to do is impute that data autoregressively. So just like you would in like a language model. I condition on the observed y's and generate the next y from the correct conditional distribution. Okay. I then condition on the y I generated, just like you condition on the next word you wrote, and I generate the next y again. Okay? I condition on the fourth y that I've generated and generate the fifth y. Right? So you always condition on the past. Okay? And if you compute a whole scenario, then under this fictional data set, you could say, hey, this article was highly engaging. Or hey, this person had diabetes in that scenario. I do it again, not so engaging. Do it again, very engaging. Okay, and the lemma that is true by definition, pretty much, is that if you generate all the y's from the correct conditional distribution, then you generated this set of y's from the correct joint distribution, and this process formed valid inference, formed a posterior set. To close here, so what this said, pretty much, and we go through in the paper with more epsilons everywhere, right? And some of the epsilons in that case, it's not that sometimes this is very stupid. It's a little interesting in this case. Epsilons don't blow up, but this is morally what this says is if you could predict the distribution of the next y well, then you can generate the sequence of y's, and you can view uncertainty quantification in certain cases as uncertainty about the missing data. And so this maps right in to quantifying uncertainty. Yeah. Close here so we've seen these two cases where sequence prediction is automatically, in a way, aligned with principles of sequential decision making. And the two use cases are quite different in how they look. In the first use case, where it's policy optimization, the sequence model is being used to imitate actions. So the thing you predict is an action. It has those semantics. And generating is literally generating a recommendation of what to do. In this case, the thing you are imitating is not your action. You're imitating something about the world, how other users would respond, how the tests would work. So in this case, the sequence model is a world model. It's telling you predictions of how the world operates. We've done it in such a way that it is measuring uncertainty you have about properties of the world. And this is kind of another way you can plug naturally into certain decision-making procedures. Okay. I'm going to sort of close here. I hope you're okay with my roundabout talk that throws together two different works. And I hope some of you can kind of continue to push this direction. Further than I can push it.
Thank you, Daniel, for the great talk. Any questions for the speaker?
Yeah, thank you for the talk. I'm thinking about the first half and your example. So, like, it seems like the improvement isn't that big if you take one step, and maybe this is your point, but like, if you use your new policy and you iterate, it seems like it would continue progressing, and maybe that's like a more realistic way that this is used. You know, you update your policy, you see how things respond, and then you continue doing this improvement step. So do you have a sense like what things will converge to if you do that? Like, is the single step version the correct way to think about it?
Great. So there's a lot of interesting open questions raised by the first part of the talk. Many of which are kind of around this direction of like, how do you overcome that shortcoming where the improvement's not so large? So there's maybe ways to amplify the improvement in a single step. I point to a few in the conclusion of the paper. And those are worth studying. The other big open question is what if you iterate, which you correctly flagged. So what I know, which isn't very deep, is if you iterate, you will keep getting weakly better, right? Just induction. The question is whether you stall. And the possible mode in which you could stall is that you could stop exploring. So if your policy becomes fairly degenerate and does so too fast, then conditioned on success, you just did the thing you always do. You know, you always act the same way, you're stuck. And you maybe have to modify the algorithm to avoid that, and I don't know how to do it. So that's a sharp question.
But it's sort of closely tied to like very traditional problems in RL multi-bandit.
It is. But there's no hyperparameters for me to pick, so I don't know. Yeah.
Hey, great talk. I actually had a question about the case study too. I was wondering if there are like any underlying assumptions about the user subset that you use, because it's also heavily dependent on, let's say, like demography, the demographic skew of like the people. For example, like filling in missing data or running the same similar articles 2 days for 2 different demographic sets. So for example, in the diabetes example, it's very objective facts or objective medical tests where you can use that to fill in the missing data to say, hey, do I have diabetes or not? But in your example, for example, the first 2 people were like older people who didn't like the article. And the third person you're guessing to fill in the missing data is a younger person who probably would love the article, but you're filling it in based on the first 2 people. Like, I just wanted some clarity on that.
It doesn't. So you're gonna, if people are very, very heterogeneous, then this news article recommendation system, the way I constructed it in the fake example, would have a bad product. Because they're going to show something that is appealing to, regardless of who you are. It wouldn't be very personalized. There's some extension where you can personalize. What I guess I'll mention is what the theory needs to make it go, though, is not the assumption that each person is the same as each other. What it needs is that if people are very heterogeneous today, they were also very heterogeneous in the historical data. Right? So that you could presumably, like offline, have learned a sequence model that already captures the patterns you're talking about. But if you end up in a world where you have a sequence model that says everybody's the same, but tomorrow some polarizing event happens and no one's the same anymore, you're in a lot of trouble. So that's the assumption.
Thanks so much for the great talk. So I have 2 questions for the first part. So the first question is, you mentioned this is for specifically success conditioning. So my understanding is like, in many settings, like this is simply like, say I'm conditioning on the success rate and I try to minimize I try to maximize the probability of the success. But in many settings, do we also need to take the unsuccessful samples also into consideration in the sense like I'm maximizing the probability of success, but also minimizing over the unsuccessful samples, and would that bring any difference into the results? And the second question is like, because you also compare it with like classical TRPO, PPO type of settings where basically my understanding is like you're penalizing over different divergence between the policy, and one is chi-square and one is chi-L divergence. Maybe I'm missing something here, but can you remark on like, say, under what setting one is more suitable than the others, and whether we can bring like propose new like divergence measures for this to be like, I guess, more flexible or like generalizable for many settings?
Yeah, so let me try to go quickly. The first question, I think as long as you actually have binary success, then it's okay. I mean, the theory, I guess, suggests it is okay to train only on the successes. That somehow, if you increase the chance of success, then you do reduce the chance of failure because it's binary. The paper has a section, though, I think this is some of what you're feeling, is that often there's success and there's failure and there's catastrophic failure. You know, and the paper has a section on what happens when there's many levels of performance that I won't go into here. To the second question, you know, this is also something that is covered in more depth in the paper. Relative to something like PPO, there's 2 big differences here. One is that the radius of the region is not a hyperparameter. It's set by the data. That's one conceptual difference. The second conceptual difference is that the constraint is penalizing you for trying new actions, but is allowing you to drop old actions. And TRPO actually goes the opposite direction. It allows you to drop nothing. The last difference, and this is where I don't know how to design something different, is success conditioning only secretly solves this problem. It secretly solves a trust region problem, but literally people do the sequence modeling thing. And so how you change the sequence modeling pseudocode to induce different optimization problems is a very interesting question that I don't understand. Okay.
Thank you. This is very interesting. So I have a question that's kind of related to the first question. Okay. So I wonder if you have like a sequence of definition of success, like for example, if like it's not binary, but instead continuous, you can like perhaps have like first a more lenient definition of success, and then have it to like be more and more stringent, and then can you like possibly have it converge to like an optimal policy?
That's very interesting. And I think that relates a little to the, okay, so I'll just flag I mean, here's what I do know about the case where the rewards are non-binary. First, there is a dumb theory reduction, where if you get a reward of 0.7, you round it to 1 with probability 0.7. Okay? And that preserves your objective. Like maximizing expected reward in the two problems is the same. Technically, it's just a matter of how much data you have. And so you could study success conditioning faithfully with this dumb rounding. But that's not what people do. People do things more like thresholding, where they assign a success if you go above 0.9, but not otherwise. But they do that only in training. In eval, they use the dense rewards. So there is this question, and there's a section in the paper with kind of a plot about this. There is this question of how high do you set the bar, right, if you do a procedure like that. And the trade-off is basically the following. If you set a very high threshold for success, then intuitively, and also in the math, you are being more discriminative in what behaviors you select for. Like intuitively, like any bozo can do medium well. But to do great, you have to be a great policy. Okay, so if you set a high threshold, you pick the great policy. Pick the great behaviors up. The problem is that in some problems, the way you get really high return is by doing something very risky that you actually don't want to do on average. And so if you pick too high a threshold, you actually pick bad actions. And so there's this delicate tension, and I don't think anybody's thought about it that carefully. They just try thresholds.
Very adventure question. There is this literature on offline reinforcement learning, which also talks about learning about the model from offline data.
Okay.
Doesn't have the conditioning aspects that you described. But in some sense, there are parallels regarding learning more about the model, not necessarily, doing the policy, learning directly, but learning the model itself. Are there some parallels between these and the offline RL for model learning?
Yes, so I mean, the decision transformer stuff it was initially introduced in an offline setting, but you're correct that it's just skipping all of that. It just says, here's the policy.
I'm interested in the use of your approach for that.
Yeah, I don't know. I mean, I think that there is a common attempt, I guess, going on to try to use the offline data to learn a world model, and then use that as a simulator to learn a policy. And then this can work very well, or it can sometimes not work very well. And I don't know that I have much to say about when it's going to be a good idea or not. I think it's a very interesting direction.